Welcome everyone to the latest talk in the Evals X Alphachives talk series. I'm Nikhil. I work as a research scientist at Evals. Today we're excited to host Alex Gu. He's a PhD student at MIT, and his research focuses on evaluating AI models on math and programming tasks, in addition to a number of other things. And he's going to be talking about that today. And his work has included a lot of like widely adopted benchmarks and tools, including LiveCodeBench, BigCodeBench, CRUXEval, LeanDojo, IneqMath, and more. And in this session, he will share his insights on how evals can inform our perspective on both capabilities and explore the challenges of AI models on these math and coding tasks. So with that, Alex, take it away.
Yeah, thank you, Nico, for the introduction. And today I'm going to talk about evaluating AI systems on coding and mathematical tasks. So first, I'm going to talk about designing evaluations. So when you're designing an evaluation, there's kind of three core components that you want to have. Right? So the first is identifying a challenge. Right? So here you want to look at the models, and you want to see what are some things that the models don't do so well, or what are some things that you think the model could be better at. Right. So the second, once you've identified the challenge, you kind of want to design the task. Right. So you want to say, what is a task that can properly measure the model's ability to do this challenge? And I think the most important part here is this third part where you want to critically study the insights. Right? A lot of these benchmarks, people see a lot of benchmarks as what model is at the very top of the leaderboard for the task. But instead, I think it's very important to kind of dive deeper into kind of comparing various models and to critically study some of these insights. So the talk is going to be in two parts. First, I'm going to talk about a few benchmarks that we've made. And this is where I'm going to talk about CRUXEval, LiveCodeBench, and IneqMath. And with these benchmarks, I'm going to kind of highlight some of the core insights that we're able to get from designing and measuring models on these benchmarks. In the second part of the talk, I'll then move to some of the challenges that face AI for coding models today. And I'm going to divide these into four parts, which are data, scale, interaction, and measurement. So to start with the benchmarks, the first benchmark I'm going to talk about is CRUXEval. So this is a benchmark we designed for execution prediction, right? So in this case, we have two separate tasks. One is called input prediction, where you have a program and you want to find an input that produces a given output. So this is kind of testing the challenge of whether models can understand and reason about code. The second part of the benchmark is output prediction, right? So this is where you want to execute a function on a given input. So in this case, we're trying to test code execution abilities. You can see at the bottom here, I'm showing an example of a function. So this is a relatively simple function. And we have an input here, and you want to predict, this is the output prediction task. What is f of this input? And in the second case, you have an output here, and you want to kind of say, what is some input that gives you this output? So we actually designed this benchmark about 2 years ago, and models are mostly able to saturate this benchmark now. But I think what the important part to kind of mention here is that this benchmark is one of the kind of ideas where we wanted to see how good are models at execution and how can models use execution to improve at code generation. And some of the ideas behind this benchmark have been used in, for example, the recent Code World model paper by Meta. So now I just kind of want to give you one of the insights that our benchmark was able to reveal about 2 years ago. Right, so 2 years ago, we had this trend where all of the models were, we had base models and we had instruct models. Right, so in this case, I'm showing some of the base models in blue. You see CodeLlama, DeepSeek, you see StartCoder here, and some of the more instruct models in orange. So these would be like WizardCoder or Find or DeepSeek instruct version. And we wanted to see whether these blue models versus these orange models, is there something that's lost or gained? Like what's kind of happening when we instruction tune these language models? So what we did is we plotted the human eval capabilities on the x-axis and the CRUXEval output prediction abilities on the y-axis. Right, so I'm just choosing output prediction relatively arbitrarily. If you look at input prediction, you'll see a similar trend. So what we actually saw is when we plotted the chart like this, we really saw three separate groups of models, right? So you might expect, maybe being better at human eval should lead to being better at CRUXEval. But this is actually not the case for all the models, right? So this is actually true for the base models, right? So for these base models, we see a positive correlation where better performance on human eval means better performance on CRUXEval. And this is kind of consistent with what you might expect. If humans pick up programming abilities, then they should improve at both cases. Now, what's interesting is looking at some of these instruction tuned models is that when they're distilled on data from GPT, you'll see that they're actually much better at human eval, but they don't actually perform as well at CRUXEval. Right, so this is kind of, we're showing that gains in human eval don't really translate to gains in CRUXEval, and so the language models are picking up better code generation abilities, but they don't really gain code understanding abilities. Right, so this is kind of different from what you might expect, and it kind of shows in a sense, you have some overfitting when you're trying to distill on this data instead of getting really generalization where you're gaining at coding abilities overall. And finally, at the time we were looking at GPT-4 as well, and we were able to see GPT-4 is good at both human eval and CRUXEval, and so it was kind of like a clear outlier compared to some of the other models that we were looking at the time. So overall, we're able to see all of these trends from this benchmark. And I think what's important here is not that the benchmark is really, I think execution ability is a nice to have thing rather than a capability that all the models need to have. But I think from the lens of execution, we're able to kind of start to separate some of the insights about generalization versus code generation. Okay, so the second benchmark I'm going to talk about is LiveCodeBench. So LiveCodeBench is a fresh and live benchmark where we have kind of fresh algorithmic problems collected from weekly contests on AtCoder, Codeforces, and LeetCode, right? Some of these competitive programming platforms. So with LiveCodeBench, I think one of the big insights is this using time as a control knob to kind of measure the model capabilities. And so before, there's this big question of how many of these, evaluations are kind of contaminated, right? And you see human eval numbers were going up. Actually, in the previous, when we were looking at CRUXEval, we saw some of these models were up to already 80 or 90%, right? And so we saw maybe it's time for kind of like a live evaluation where we look at problems from, older problems and newer problems and kind of compare, the model's performance over time. So when we looked at that, you kind of see this big gap between the older kind of versions and the newer versions, right? So if you look at this GPT-4 cutoff date here, you'll see that kind of GPT-4's performance is plateauing and dropping, after this cutoff date. Whereas if you look at DeepSeek Instruct, kind of some of the blue line here, you see after September, which is the DeepSeek Instruct release date. If you look at problems after that, you'll kind of see, that the performance goes down compared to the old performance. Right, and so this is kind of for a control. If you look at GPT-4 Turbo, the performance is actually relatively stable over the period. So this kind of highlights that contamination is actually a relatively big problem. And actually through our evaluation, if you look at our website, we have, you can scroll through a certain time period and see how good the models are at that specific time period. And if you do that, you can kind of see which of the models are actually kind of overfitting to the older problems and which of the models are really kind of evaluated fresh, trained on good new problems and are able to generalize to unseen competitive programming tasks. We also see a similar story as we saw with CRUXEval, where if we look at, let's say, the easy subset of LiveCodeBench compared to human eval plus, we plot PASAT1 on the x-axis for LCB versus human eval. And what we're really seeing is we have these clusters of green models, right? So for the green models, you're seeing PASAT1 for LiveCodeBench and PASAT1 for human eval plus are relatively correlated. Right, but then we have some of these red models here, like DeepSeek model, which was released about in September. You see a stark decrease in performance, after August, right? And so, you can kind of see that these models are starting to be much more kind of overfitted for human eval compared to LiveCodeBench. And at that time when we released our benchmark, it was another fresh benchmark, kind of untouched before, untrained on, and so we could really detect the overfitting of which models were kind of trying to overfit to the benchmarks versus which models were really performing well. Okay, so this is our LiveCodeBench benchmark. And finally, I'm going to talk about a benchmark called IneqMath, which is a benchmark that we use to try to measure the ability of language models to solve inequality proofs. So in this case, what we do is we take a bunch of Olympiad IMO level inequality proofs, and we reformulate them into two verifiable subtasks. So we have bound estimation to the left, where maybe you have an inequality and you want to guess, find the largest C such that this inequality always holds true. We also have relation prediction, where you have two sides of an inequality and you want to determine the relationship, is the left-hand side greater than or equal to, or less than or equal to the right-hand side. So here's an example of one of the testing examples in our task. Here's a bound problem. It's a Olympiad level problem where we try to test the abilities of models to kind of solve these problems. So with this benchmark, I'm going to kind of share two insights. The first one is this soundness gap. right? So the soundness gap is kind of referring to the fact that the language models can actually guess the right answer a lot of the time. So in all four of these plots, on the left, the higher bar, the darker bar, you see the answer accuracy. And so answer accuracy is how well can the model solve the problem and get the answer to the inequality. Now on the right, we have the overall accuracy, and this is not just getting the answer right, but also being able to provide correct reasoning for the answer. And so for this, we use a bunch of verifiable judges, and you see across the board, all the models show a very large gap between the answer accuracy and the overall accuracy. And so this kind of highlights this trend where the language models are very good at guessing the right answer. If you ask it to do like a multiple choice question, it really knows intuitively, maybe from seeing similar data, maybe from seeing patterns, it knows what the answer is. But if you start to look into their reasoning, you'll find there's a lot of unsound steps. You'll find a lot of hallucinations, you see a lot of false logic, and you'll find the model actually doesn't really know how to prove anything. Right, and so, for example, if you look at Grok 3, answer accuracy versus overall accuracy, you see a very, very large drop between 54.5% all the way to 3.5% for overall accuracy. The second insight our benchmark was able to reveal is that even adding thinking doesn't really solve these problems. So we added a lot of token limits. We tried 5K all the way up to 40K, and about 5K to 10K, you do see performance gains up to 20K even as well. But if you try longer from 20K to 40K, you see things are mostly saturating and it's not really improving, even if you give it longer chain of thoughts. So what we're kind of seeing is the reason for this is, I believe, is because the models are kind of getting into these patterns where it's thinking kind of unnecessarily. It's trying to see what it thought that was helpful, but it's unable to actually come up with anything new, and it doesn't solve something that previously with, let's say, 20K completion tokens, it was able to solve. So this is kind of the first part of the talk, some of the benchmarks that we were coming up with. And now I'm going to turn to the challenges part, right? And so I want to emphasize that in AI for coding, there's many unsolved and unmeasured frontiers, in this entire space of AI for coding and software engineering. And so I think, you guys and all of the community, there's still a lot to go. There's still many evaluations that can be developed in order to progress the field and improve AI for code. So I'm going to group this into kind of 4 categories, answering this big question of where do today's AI systems fail when it comes to AI for software engineering? And these categories are data, scale, interaction, and measurement. So when it comes to data, we all know that models are very good when it comes to reciting things that it's seen before. But actually, coding relies on a lot of generalization. And when you ask models to do tasks they haven't seen before, they'll start to trip up. So as one example of this, you'll see that, let's see, Gamma 3 makes fundamental syntax errors in this language called Triton. And this is a GPU programming language that's used to write kernels. So we ask it to write a dot product kernel, and actually it makes a very fundamental mistake of using actual dot products. And if you've written Triton, you'll know that this language actually communicates with loads, stores, and batch operations instead of dot products. And so this ends up being completely invalid syntax. And my guess would be, this type of behavior is probably a result of borrowing constructs from higher level languages, where this indexing to do a dot product notation is actually very common. Now, another example from a language called Lean. So here I asked Claude 3.7 Sonnet to prove a theorem that says there's infinitely many primes that's 1 mod 6. So this theorem is actually a direct application of Dirichlet's theorem for arithmetic progressions. But unlike the previous example, the syntax is perfectly valid Lean syntax, right? So the model was able to get the problem statement correct. It even knows how to prove the theorem, knows which theorem to use to prove it. But the issue is when you ask it to write Lean code, now it's hallucinating both the name of the theorem that doesn't actually exist, and it also tried to guess how to apply the theorem. And for those that are interested, there actually is a Dirichlet's theorem in Lean. It's just that the model was unable to find it. And it's way less natural than kind of the syntax that it hallucinated, which feels like it's more correct based on maybe knowledge of natural language and also its limited knowledge of Lean. So a separate anecdote about Lean is that around 2021, everyone was using this version of Lean 3, right? So kind of like, Python 2 before. And then the community in Lean 3 had already contributed 500,000 lines of code to this library called MathLib, which was a very big ongoing project that makes it easy to formalize a bunch of mathematics. But then, people realized that Lean 3 had all these major shortcomings like metaprogramming. And so there's this big project to port Lean 3 to Lean 4. So Lean 4 now had its stable release in 2023, and it's the version of Lean we all love today. But these library version updates also trip up models a lot, right? So here I explicitly asked O3 Mini to write a Lean 4 proof. It still reverts to Lean 3 syntax. And just as a side note, Lean 3 and Lean 4 are virtually incompatible. So even though Lean 4 has been around for 2 to 3 years already, there's still a bunch of Lean 3 in the model training data. And it's the predominant version, it was used for many years. And so there's more kind of Lean 3 tokens compared to Lean 4 tokens. So dealing with these version updates can be relatively hard for several reasons. You can tell Lean 3 from Lean 4 relatively easily, but libraries and APIs usually undergo more incremental version updates, right? Like telling a certain version of NumPy from the next version up. And even though if you know what version you're working with, adapting and knowing what functions are available in that version is usually not really compartmentalized cleanly for the models. And so finally, a crucial aspect of adaptation is adopting these new paradigms and being able to leverage new releases even before massive amounts of training data is there to kind of learn from. And the fact that there even is a paradigm shift signifies it's probably useful for something, right? And like a more alarming case, is let's say when features releases are because of these security vulnerabilities in older versions, right? Because if you have security issues and the models don't really learn older versus newer version, then you may see kind of insecure code that's being generated. And just as an example of this, in Java 17, there's actually an update for how to do more secure random number generation. But there's a paper showing that these language models still would default to the insecure versions before that release. So the whole point of these version updates is to try to fix things that were worse in previous versions, but today's models still really lag in the time it takes to adopt and switch between the various versions. And the last data-related challenge I want to talk about is these high logical complexity out-of-distribution domains. So these are like the tasks that are even challenging for human programmers, requiring high levels of algorithmic ingenuity and complex logic. In these domains, the search space can be large. You have highly non-obvious algorithms, and you can even have very limited verification and intermediate rewards. So, in this case, I think there's a lot of benchmarks and evaluations that can be really created to really test these, the most challenging human programming tasks. So I think it's really worth thinking about, what it would take both to evaluate these systems and also for today's AI systems to successfully conquer some of these complex domains. So the next challenge I want to talk about is scale. So this is kind of the challenges we face when we deal with code bases millions of lines long, where there's complex algorithms and intricately connected components. When it comes to this issue, one point I really want to drive home is I think purely scaling up model size and data will probably not be enough. So to understand why, maybe let's explore some of these challenges in more depth. So the first one is dealing with large scopes and long contexts. And as a community, quadratic attention has been kind of a blocker to scalability, and performance is still generally degrading as contexts get longer. So the most popular way to mitigate this is retrieval augmented generation, but we think it's insufficient for several reasons. So first, retrievers are usually syntax-based. So here's an experiment where we took a few hundred code snippets, each of which had 3 versions in Go, Python, and C#. When we plotted their embeddings, we see the clusters are dominated by syntax rather than semantics. And you see that semantically equivalent code in different languages often ends up being far apart. And that makes it hard to find retrievals that have actually relevant semantic information. The second thing is that using generation can actually be a challenging code reuse task, where each retrieval provides a different part of relevant information, and all this information needs to be pieced together and altered to fit the context of the current code base. So whether you use retrieval or not, writing code at large scopes requires a general semantic understanding of the code base, and I think this is still lacking in today's models. Finding techniques to improve semantic code understanding is, still a relatively big challenge, and so is creating, these really genuine evaluations that are able to test how good are models at long contexts and how good are models at retrieval. Another of these tasks is long horizon code planning. So in this case, it's related to this crucial challenge of managing code bases at large scale. So you need to design both code abstractions and data representations that are reusable and cater to the needs of the application at hand. While there's many ways to make things work, good abstractions will really give users a very simple mental model of how these large code bases are pieced together. A separate related abstraction design is modularity and code quality. So there's this old saying in software engineering known as 3 strikes and you refactor. And what it means is if you take a piece of code, you duplicate it 3 times, it's time to turn it into a module, because then it's easier to maintain in case things are changing. Maintaining good modularity and code quality makes it much easier to succeed in the long term to avoid technical debt. And success in these 2 facets usually can't be codified into hard and fast rules. right? So being good at code planning usually comes with a lot of experience. You need to see all these examples of abstractions that don't work out. You need to try these designs before finding one that finally seems natural. And so you can't really encode them as a loss function. And so I think this is one of the exciting things, which you have an open question of both how can you measure this and provide rewards, as well as how can you really evaluate whether models are really getting better at modularity and code quality. Finally, I want to mention this effective tool usage. I think while humans often rely on external tools when coding, you have these models which don't really use IDE search, for example, or profilers, or things like even Vim and Emacs, right? So AI coding systems don't rely on anything beyond like an interpreter or execution engine. And this is kind of because using tools effectively is relatively difficult. And agents need to learn what tool to use, when to use the tool, how to set up the tool, and even how to interpret the results of the tool. So this is another case where you can come up with like a tool usage, software engineering benchmark that could potentially, really measure the ability to use different tools. Maybe one tool models know how to use. Maybe some of these lower resource tools, niche tools, the models are less good at. And the next challenge I want to talk about is interaction. So this is a challenge that's actually very difficult to measure because we want to design AI coding systems that are interacting seamlessly with us instead of introducing additional overhead. So a representative example from CRUXEval, there's an issue that asks for a code base to support a new input format because there's a lot of data in that format. So a seasoned engineer, when you see an issue like this, you know to implement both read and write operations, which are known as deserialization and serialization. But models in this case, they only implemented a read function, making it impossible to write data in this format. This is highlighting a common issue when working with coding models. We give these models a vague specification that should be clear to another human, but the model will usually interpret things in a completely different way. And this is partially due to the fact that language and code are at different levels of abstraction. And so it's impossible for us to always specify everything completely precisely. And even beyond that, I think a bigger challenge is that today's human AI interface is very restricted. And if you think about driving, right? So in the previous decades, cars have increasingly added mechanisms like cruise control and collision warning systems. And each of these enhancements marginally increased our experience of driving. But the real paradigm shift here is self-driving, right? Which all you have to do is you just have to think about the high level of where you want to go. And you can just monitor the car to make sure it's not going crazy. And I really think that AI for code is at a very similar point here. Today, we have these small little IDE enhancements that can complete our functions properly. But soon, I think we can imagine a world where AI does all this scaffolding. We'll have this self-driving car moment. And I think it's important to think about what the design of this looks like, in addition to how we know whether a design is correct or incorrect. Finally, I'm going to move to measurement. Right, so in measurement, we're kind of talking about what is the right way to evaluate AI for coding systems. And so I think here are the three kind of big issues that kind of permeate some of the evaluations, not just for coding, for math, but also in general for things like human eval, CRUXEval, so on. And so the first thing is task diversity. There's all these different tasks in AI for software engineering, but we're mostly still focused on just code generation everywhere. Right, so code generation is one of the predominant tasks that are here everywhere. And I think the reason we measure code generation rather than all these other tasks is that these problems are actually easy to source and evaluate. Right, they're all over GitHub and all over these competitive programming platforms. And so function level tasks like human eval and BPP and code contests are very easy to source and take and evaluate. But now that the models have begun to saturate all of these things, I think it's time to be deliberate about how we evaluate our models. Right? So instead of generating code in one go, these future AI systems need to tackle more complex tasks like generating test cases or refactoring code or even formally verifying code. The second issue that I talked about before is contamination. There's a time a few years ago where people claimed that the models could solve competitive programming problems, right? And so then we as a community realized that the performance on older problems was way better than the newer ones. Similarly, I would say benchmarks like CRUXEval are probably also open source from openly available GitHub data. And a lot of the solution patches are actually right there on the GitHub page. So recently, there was this GitHub issue on CRUXEval that kind of shows some of these newer models are looking at the patches, kind of searching things online and finding some of the issues of the tasks that they're trying to solve. Right. And so in these cases, we want to prevent these type of behaviors if we want to really correctly evaluate the behavior of these models to solve these tasks from scratch without having seen it before. But beyond these, I think the biggest challenge here in measurement is actually construct validity. And this has to do with whether our benchmarks are actually measuring the thing that we want them to. So automated testing is usually, if you use unit testing, it's usually pretty nice and very clean. But there's a lot of things that I actually can't measure, like simulating multi-turn code generation or writing code that's clean and maintainable. And another aspect, is where I was talking about this human AI collaboration piece, where if you don't actually have a human in the loop, it's very hard to measure whether models are able to effectively collaborate with humans. And we talked to part of the cognition team, and one of the issues that they mentioned is some of these automated benchmarks really don't give very much signal when it comes to whether users are enjoying the user experience with the models that they're developing. And that's because, for something like the issue I mentioned before, where the models are able to actually do the task, but the models just kind of need a little nudge from the human, like in the read-write example, where if the human would say, okay, you also need the write method in this task, then the model would say, okay, I know how to implement that. It's just that I didn't know that you actually wanted this from the behaviors. And so the model certainly knows how to implement the methods, and I would say the model actually has the skill, right? So the overall capability of the model is very good, but the level of human feedback here is not really integrated into our evaluations. And this can actually make it very hard to think about research questions involving the impact of human feedback. So, despite all this remarkable progress, I first show 3 benchmarks that are still measuring and exposing some of these failure modes and insights of these models. So for CRUXEval, it's an execution benchmark where we're able to show the difference between execution behavior and generation behavior. In LiveCodeBench, we really highlighted contamination. But beyond contamination, we also have other tasks in the benchmark. We don't have generation only, we also have execution, repair, and test output generation. And for IneqMath, we really showed that when we have verifiable rewards, when we have like an answer checking, these models look like they're solving these tasks very strongly. But when we start to actually look at their proofs, we start to see these gaps where we see that when the model tries to write a proof for the problem, it's failing in multiple ways. Then I talk about the challenges. In the challenges, we have data. We have scale, which is when we scale up to larger scopes and larger contexts. We have interaction, which is the problem of whether AI can collaborate effectively with humans. And finally, we have measurement, which kind of has to do with how we really evaluate and are able to test and improve the capabilities of language models. So that's all for my talk today, and I'm now happy to take some questions.
Cool. Awesome. Thank you, Alex. I think that was a great talk and a lot of thought-provoking directions for the future investigation. So yeah, as we move on to Q&A, if you have questions, please use the Q&A feature at the bottom right to post questions. And we can unmute people to ask them when it's your turn. I have a few that I'll kick off the discussion with. So one of the things that I was thinking about during the talk was in the, for example, IneqMath discussion, you mentioned there's this degradation when you look at like accuracy versus the actual reasoning chains that lead to that answer. It seems quite interesting to me. I guess 2 questions. One is, do you have any guesses for why this might happen? And then second one is, this seems like a useful evaluation mechanism to apply to a whole class of benchmarks. And so I was wondering if you have thoughts on that.
Yeah, so for the first question, I think there's many reasons why solving a problem is much easier than writing a proof for the problem. For example, if you want to prove a problem, you at least need to know the answer, right? And there's many ways of actually getting the correct answer without proving the problem. One example is if you look at some of the IMO grading criteria, you'll see that out of 7 points, getting the answer correct is only 1 out of 7, right? Because just getting the answer, you can try all kinds of weird techniques. You can like try easy examples. You can, for inequalities, you can even plug in numbers to see which side is bigger, and that'll eliminate kind of some class of answers. But also, a lot of these problems in the literature you've seen, like textbook problems, you usually, or like exam problems, you'll see kind of these problem statements, and then you'll see solutions where at the end you have this very nice boxed clean format where it says the answer is in this box. And when the model sees all of that, it's probably getting a very clear association between here's the problem and here's the answer. And if you just modify the numbers a bit, or you modify like the way the statement is written, you don't really need a high level understanding of the proof to be able to get the answer, right? And so I think because of these reasons, the model is looking at the problem, the model is looking at the answer. It's much less, let's say, tokens or reasoning effort to get the answer compared to getting the whole proof. as to your second question about, I think evaluating this framework, changing this framework to adapt to some of the other scenarios, I think that, yeah, I agree that there's a lot of kind of more nuanced abilities of these models. And I do think that I think looking at a single number is very useful when it comes to saying, okay, I want a large picture insights for these models are good at this type of problems. If you're looking at categories, let's say like LiveCodeBench versus SweetBench, I think that could be a useful evaluation to say, okay, this model is really optimized for LiveCodeBench, but it's terrible at SweetBench, or vice versa, where the model is really good at SweetBench, but it doesn't really have, let's say, these reasoning, competitive programming, kind of more detailed algorithmic thinking abilities of LiveCodeBench, right? And so I think looking at those single numbers in these categories is useful, but I do think to really understand what's happening with a particular benchmark, you want to look at the samples, you want to kind of have a dichotomy of what are the specific things that I really want to measure. Where in this case, looking at answer accuracy does give some signal, right? Like better models, the proprietary models are better than the open source chat models at, almost both of these, right? So if you look at answer accuracy, you can already see like there is a difference between, let's say, Gemini 2.5 Pro and like Quant 2.5, and it's relatively apparent. But then if you look at the overall accuracy, it'll be even more apparent, where it's like 43.5 compared to 2.5, right? And so in this case, you can see that Quen is still it does have abilities to do math reasoning. It's just that the abilities to actually write the proofs are almost non-existent. Whereas it can still solve a lot of these problems correctly, right? So if you give it like a math problem, you'll still be able to get the answer a lot of the time. So I think there's benefit to kind of having multiple categories, and each of the categories kind of highlights a certain benefit or weakness of every model.
Got it. Yeah, it does seem useful also in the sense that if the discrepancy is super high, then it seems like the model is guessing more than being able to prove it. So maybe the discrepancy can help you identify these kinds of weaknesses.
Yeah, yeah. I think, yeah, looking at the discrepancy, it's kind of apparent that, there's an obvious reconstruction of how can we bridge the gap between knowing the answer, just the answer correct, and also being able to really move towards these proofs, right? And it's pretty clear that we as a community, looking at something like Quen, Llama 4, are really kind of over-indexing towards just getting these verifiable answers correct. And I do think this is an artifact of when you do reinforcement learning, you need a verifiable artifact, right? And so because you have this verifiable number, it's much easier to get the number correct than to get the whole proof correct. And so this kind of signals we need to have a shift between just this one number proof correctness and this entirety correctness.
Got it. Yeah, cool. That's pretty helpful. And then my second question was on the human AI collaboration point that you made.
Yeah.
I think like it's interesting that you mentioned it's almost like you were trying to elicit abilities from these models as humans, and maybe they just need the right context from us when we're prompting them.
Yeah.
But then automated evals don't really capture this problem because they're just either a single prompt at the beginning and then an evaluation mechanism, or it's fully automated, and so it's hard to make progress. I guess the closest solution I've seen in the literature is maybe like evaluating at substeps. So you maybe have a model that does something, and then you evaluate it like a third of the way along to the full solution, and then you can maybe like even introduce like user personas or something to prompt it correctly. But then that seems bad for determinism. So yeah, I'm curious if you've seen works that kind of address this problem or have insights on how to do that.
Yeah, I would say, determinism is not something that I think is required for an evaluation for human AI collaboration, just because even humans don't have determinism, right? Like if one day if I got lots of sleep, I ate good breakfast, now I'm feeling really good, and I learn much faster than maybe another day where I stayed up late the night before and, I didn't have anything to eat and I was having, all these problems, right? So I think in terms of trying to figure out a good interface for human AI collaboration, I do think personas is a very strong way to go about this, right? I think using personas is a powerful tool, but I think the issue is that you need to really figure out whether these personas are realistic. And it's every time you have like a proxy evaluation, evaluations are already a proxy for a certain real world task. In the same way that SweetBench is a proxy for software engineering abilities, and LiveCodeBench is a proxy for how good are these models at doing these context coding algorithmic problems. And I think that in a similar way, if you have a persona or you have like checkpoints, being able to measure these specific abilities, I think is very important. Right. So for example, in this fake specifications case, I think you could have a evaluation that says, how do models interpret these specifications? Are they able to extract the correct kind of inferences of the same things that the users would extract? Right. So maybe you would take a specification, you would ask a model to say, here are 5 things I think need to be true. Then you go and ask a human, here are some things that need to be true. And then you kind of compare them and see, okay, are the models really hitting all the implementation points that the human would come up with? Right, and I think like this could be one way of measuring human AI collaboration. In terms of the interface, you could also say, it's kind of like I've seen some work in education where people are taking these persona students. You have students who are very quick learners. You have students who maybe need a bit of time to learn some of these things, and so you prompt the model to say take on these personas. And the way you train a model to probably educate like a quicker student may be different from the way you train a model to educate a student who may need more handholding and assistance. And so in this case, you can kind of evaluate like, okay, is there a unified solution that works for everyone? Probably not. And so then you can kind of test, okay, well, this model has this advantage for maybe if you develop a model only for some of those quicker students, it will not perform as well for the other group. Whereas vice versa, you develop this model to have various capabilities. And for coding, you have it's strong at these points, it's not strong at these points. And it's very similar like when you're doing IDE design, right? Like some people enjoy using cursor, where you have this like IDE type model. Some people enjoy more of like a cognition Devon model, where you kind of just give it the task, you kind of hand it off to this model, it goes off and thinks, and then it comes back to you with some questions, right? And I think like everyone has a different paradigm, and I do think what's missing is like a good evaluation of this paradigm suits this sort of person, or this paradigm suits this sort of task, whereas maybe this other paradigm is kind of lacking.
Okay, yeah, that does make sense. So the eval is kind of more tailored to the person and their skills and personality.
Yeah.
Yeah, that makes sense. Cool. I do have a lot more questions, but I see a couple in the chat. So I see a question from Jacob, which I can ask, and then next we'll have Ryan ask his question, and then I see another one from an anonymous participant. So Jacob asks, the two solutions I've seen for large corpora of specialized data are context engineering, that is like RAG and indexing, or fine-tuning on the specialized corpus. Do you have any thoughts or opinions on which one makes sense, and or where the other solution paths are available?
Yeah, so I think there's a lot of ways that people are trying to deal with large corpuses of specialized data. I remember a lot of there are a few companies, who are trying this long shot mission, which is I'm going to fit all the data into my context. Like I'm not even going to use RAG. I'm not going to do fine tuning. I'm going to fit everything into my long context, and I'm going to get like a super nice long context model that's able to make use of the context. I think it's a potential path. It hasn't turned out to work yet, but I do think it's possible. If we figure out long context, as a both research and engineering problem, that we're able to kind of unlock this path. When it comes to RAG and indexing, I think this is a much more kind of intuitive way of solving these problems. In the sense that you need to look for the piece of code, you need to find the piece of code, you need to use the piece of code. I think RAG can be useful for certain cases when, let's say, you're looking at an implementation and you need to know what are some details of the implementation. Like if you're implementing an algorithm in, let's say, C, and you're looking for a similar algorithm in Java and it already exists, then it doesn't matter if it's a low context problem if what you only need is the algorithm, right? So in this case, it's RAG works perfectly as long as you're able to retrieve the correct example. There's also fine tuning, right? As you mentioned, I think fine tuning on like a specialized corpus. This is a much more expensive method compared to, I would say, RAG indexing or even putting everything in long context, because you really need to fine tune and adapt to the corpus. And I would say that it makes sense if you have like let's say you have a custom language for your infrastructure, which a lot of companies do. And so what they do is they probably have domain specific models that are already fine-tuned on all their documentation. It's fine-tuned on previous code samples of that language. And so it knows how to write code in that language better than, let's say, any open source or proprietary model can at API time, right? And so if you are able to fine tune your model, there's a lot of benefit you can gain beyond, I would say, RAG indexing and long context. But I do think that this can be expensive. And the other issue is that we haven't really figured out how to fine tune in a way that preserves things like version updates, right? Like before I was talking about going from Lean 3 to Lean 4, I'm sure all these models have been trained in a way that's seen both Lean 3 and Lean 4. But then what if maybe in a few years later, if Lean 5 comes out, right? And then you're stuck with all this Lean 3 and Lean 4 code. And then you need to go and figure out like, okay, I just fine tuned on Lean 4 point, let's say like, I don't know, 4.30, which may come out in a few months. Now Lean 5 comes out, and what do I need to do? I need to go in and like fine tune again. Right, so I think fine tune could be a potentially slow process where you need to really figure out what is the way to fine tune so that you're retaining all the necessary information bits, but you're not really forgetting the things that uh, are still very useful. And like, but you do want to forget the kind of version changes that are really changing the API formats, because sometimes you call the function in a different way in the new version compared to the older version.
That does make sense. I think the next question is from Ryan. Ryan, do you want to unmute yourself?
Yeah, thanks for the talk, Alex. This is really instructive. Yeah, my question is, have you actually looked at the differences between questions in different versions of LCB? Because I'm assuming a lot of them are actually based on the same algorithms or question types. And so I'm curious what if the difference could be replicated by just some synthetic perturbation, and you might see the same trend, or maybe there's some more fundamental difference which the models are not generalizing to with each successive iteration.
Yeah, so I think the difference between successive iterations is, so I think it's all in the same distribution. And you can think of it like this, right? So every time you have contests, you have people writing these contest problems, and it's all written by the same distributions of humans who know how to do competitive programming or leak code, interview questions, interview prep, all these things, right? So I think the distribution pool is all kind of one very big uniform distribution. I do think the reason models are overfitting on previous iterations is because they're actually training on the exact problems, right? So there's a bunch of experiments for, let's say, human eval, where you just give it like 10 tokens, the first 10 tokens of the problem statement, and it's even able to recite the exact problem statement in a way that humans would have not be able to do. But I do think, there's the synthetic perturbation question, I think, is really interesting, because it's kind of saying, do the models really understand the true distribution of, like, are the models really able to solve the problem because it's, using reasoning, or is the model able to solve the problem because it was able to kind of memorize the problem? And I do think, the models are able to solve the problem because of reasoning, and it's not just strict memorization. One experiment we did when we were doing CRUXEval is we actually, instead of taking the functions to do execution, we just anonymize the variable names so that it's guaranteed that the models would have never seen that before. And we found the accuracy drop is very, very slight. The models really did have these execution abilities. And, for that benchmark, okay, I think a lot of the samples, they were all model generated, so they weren't really kind of things that were on the internet that you could train on. But in the case of LiveCodeBench, I think I don't think changing the statement slightly is going to cause meaningful accuracy differences. But I do think the interesting thing is whether you can take problems and make synthetic perturbations and come up with new interesting problems that are significantly different than the old problems. I think like taking an old problem, using it as a seed problem, and trying to develop a new problem based on that. There's a paper from, I think, Princeton called Math Squared, and what they did is they took the math benchmark, they took like 2 problems, and they combined the key ideas, and then they created a new problem based on that, and they found it's kind of much more challenging, and they kind of measure the compositional reasoning. I think that can be interesting as a potential synthetic perturbation way of creating new problems. But in general, I do think the models are relatively robustly able to solve, at least today's frontier models, a lot of these problems. And so I think unless we come up with synthetic perturbations to really significantly increase the difficulty of the problems, I don't think that this is going to cause big differences in the accuracy.
Cool. There's a couple of questions from an anonymous participant. In the interest of time, I'll pick one, and then maybe we can come back to the remaining ones after. So the question is, what's the gap between informal math reasoning and formal proof today? I'm guessing this question means the current status of what models are capable of in terms of informal proof versus formal proof.
Yeah, so in this case, I would say it's relatively difficult to actually measure the informal mathematical reasoning in a way that's accurate. So for our IneqMath benchmark, we were using kind of stepwise judges to measure the ability of these models to do informal reasoning. I think recently there's been a few more works along this direction, but I do think this is still an area that's kind of under active investigation in terms of building good benchmarks to do it. In terms of formal proof, so I didn't talk about it today, but there's a lot of things trying to prove theorems in Lean, which is this formal programming language. And for formal proofs, I think the big difference is that the models need to really understand the syntax of Lean and be able to write the proof in a step-by-step format that's correct. I do think the models are currently, if you look at like the same benchmark, for example, and you compare informal abilities to formal abilities, I would say the models are still drastically better at informal than formal. But I do think formal is kind of catching up because we're the community. We are finding ways to really improve formalization. We are seeing that things like Godel prover and seed prover, and there's a new Hilbert prover. They're able to already score relatively high scores on Putnam Bench, which is one of these kind of mathematical computation benchmarks. And I do think, if you look at these gaps, the gap is decreasing. The models are getting stronger at formal proofs. The community is getting larger in terms of both infrastructure and support for some of these formal methods. And so I do think the gap before, which is due to lack of data and lack of efforts, is starting to get closer and closer.
Jacob asks, how did you evaluate the step-by-step reasoning of the inequality benchmark? Was it LLM as a judge or a formal prover of some sort?
Yeah, so in the IneqMath, this benchmark, what we did is we looked at some of the proofs that are created by the models, and then we noticed some of these common failure modes. And so we use kind of different judges to detect some of these failure modes. And at the end, we pooled all the judges together, and we would say like, okay, do you have so one of the judges is like a kind of incorrect reasoning judge. It will kind of look at step-by-step reasoning, and it would see whether, let's say, adjacent lines are logic that's completely incorrect. We had like a kind of trial by numbers judge where we would just see if the model was just plugging numbers in and using that as like a proxy proof, even though we explicitly said not to do that. And so we combine all of these judges together. They're all LLM-based judges, and a step-by-step reasoning would only be counted correct if all the judges passed and there's no kind of issues. And in order to make sure that the judges are actually accurate, we also did a trial where we took some problems. A human would label the numbers and the proofs with whether they kind of satisfy some of these error cases. And then we found that the match between the humans and the LLM judges was actually relatively good. But I do want to remark that it was only relatively good because the proofs made by these models specifically are not like the ones with very subtle errors. I think if you had a different distribution of proofs where every proof had a very, very small error, I think that would be a case where our method actually would not work very well compared to these LLM generated proofs, which usually if it's wrong in a relatively egregious way. And so that's why the judge is able to be very effective in terms of detecting the issues with the proofs.
Got it. So like one big egregious issue rather than like minor issues that sort of pile up.
Yeah, not necessarily one big egregious issue. It's just that like when it's wrong, like a human can usually just spot look at the proof and very easily in less than 30 seconds, I would say, detect it's wrong versus like some of the proofs for, I don't know if you ever like TA'd a course before, but you'll find a lot of the students are going to submit proofs that are, they look relatively good, but it's actually kind of, there's just like an inequality sign flipped. And I think things like this, it may be kind of difficult for models to really detect kind of these subtler errors.
Thanks. There's one question from Daryl that I see. Daryl, I'm going to unmute you if you want to ask your question.
Yes, thank you so much. My question is, when it comes to human AI collaboration, have you done some studies or measurements on when an AI agent presents data such as Excel formulas, lambdas, Python, and Excel? Does it have the capabilities to have the agent be able to read it back to the human, or in some way understand orthogonal reasoning in that way when it comes to that environment?
Yeah, so we haven't really played with human AI collaboration too much in my own research, but I do think it's a very interesting question of how you present the specification or implementation to the AI, and how this is going to affect what the AI gives back to you, right? So like the way we right now interact with AI, I would say the majority of people, they will go into like ChatGPT or some model. They will say, here's a specification. It will be very vague. It will maybe probably have some typos, some errors. They'll like paste their code in, and then they will say, okay, I have this bug. Maybe I will paste the execution message, and can you fix my code, right? Whereas like a very well-written specification, you could spend like an hour writing a specification about this is the exact thing I want in my program. Here are some tests for you to try out. Here's a template that I already have. Here's some documentation that's written by, maybe some product manager. It takes a long time to write like a very precise specification. And if you give the model that compared to if you give the model like a 10-second summary of what you asked of it, I think it will give you very different results. And I do also think in terms of the programming language, there's definitely going to be differences where if you ask for an algorithm written in something like a very, very low resource language compared to a higher resource language, like maybe the same algorithm in like Python versus I don't know, like OCaml or something, you'll probably see that the agent does much better if you ask it to do Python compared to OCaml. And so, that could also be a potential trade-off where you say, even though my code base is written in OCaml, maybe the thing to do is to ask it to write it in Python first so that you can kind of see like what are the design decisions that it takes to do there. And then you can personally, as an engineer, go back and you don't need to rely on the model to do that translation step because, maybe that's your particular expertise. So I think for the human-AI collaboration, I think like the way you specify really matters. If you say, in the previous case, if you say I'm like a expert at translating Python to OCaml, then just give me it in Python. It's perfectly happy to do that. Versus if you say I don't know any OCaml, but I'm like really good at Python, maybe you will actually want it to write the OCaml because in this case, the way the model wants to be used is it doesn't really need to generate the Python code because maybe you already know how to do that.
Cool. Yeah, I think I'll ask one last question. We can close with that.
Okay.
I think one of the things that was interesting to me was this versioning issue. So especially with code or even with lean evals.
Yeah.
I was wondering like what your thoughts are on kind of like retrieval as a mechanism to address that, maybe like with web search or providing the documentation to the models. And I suspect this will be worse than kind of like retraining or fine-tuning the model on the new data. But as an evaluation mechanism, that seems reasonable. So I was wondering if you had thoughts on that.
Yeah, I think if you want to evaluate this, when we want to evaluate version updates, there is this, core question of retrieval versus fine tuning for new version updates, right? And I think there's, you could definitely do a very good evaluation work to say, to say whether the hypothesis that you just, made was actually true. I would also believe a similar thing where retrieval is able to really give you gains on like easy syntax fixes. If you just retrieve the documentation of this function and it was in like a different version before, I think that could be very helpful. But sometimes, you don't even know like what function changed between versions, right? Like the only way you know that is, let's say, a lot of the times I'm writing some, NumPy functions or matplotlib functions, and I'll find like the way I wrote it, it doesn't give me what I want. And then I'll look and find, oh, between this version and the previous version, there's some kind of big incompatibility issue that changed the API completely. So I would say in cases like that, that's when maybe you do want to do a retraining because you don't know which parts of the API were changed, but you just want to completely erase all the old and outdated data from the model at all. So in that case, I would say, yeah, for evaluation, you can probably take some samples where the API changed a lot versus the API just changed a little bit and see if the model is able to kind of learn that from retrieval. And if not, I would guess that you probably need a full fine tuning or at least maybe like a simple LoRa, a few iterations on just the things that were different.
That makes sense. Yeah. I guess you don't even know that a function might have been changed. So there's no way you can reasonably retrieve it unless you like read through the whole docs page and identify that. Makes sense. Yeah, cool. I think we'll end here. Thank you so much, Alex, for the great talk. I think many thought-provoking insights. For people who are interested, that we have our next talk is by Valentin Hoffman. He's going to talk about fluid language model benchmarking, which is a way to evaluate language models by considering their relative capabilities. for items in the benchmark. So we'll send out an announcement for that as well. Yeah, thank you so much, everyone, for joining, and see you next time.
Thanks.